Welcome back. We've got kind of a shorter lesson today. This is going to be a lesson about sigma notation and Riemann sums. In the previous lesson, we used the phrase Riemann sum. We defined that towards the end, or at least we said that the sums that we were looking at were examples of Riemann sums. But anyway, we have a new notation to introduce called sigma notation, and we're going to revisit Riemann sums. So let's get started. So, sigma notation and Riemann sums. I'll tell you that sigma is a Greek letter, and Riemann is the last name of a mathematician. So, we've got a notation named after the letter that we use, and these sums are named after this mathematician. So, let's start with the notation. It's possible you might have seen this before in an algebra class at some point. The Greek letter sigma which looks like this, stands for sum. In the context that we're going to use it in, it's kind of an abbreviation for the word sum. By the way, there's an uppercase Greek letter sigma and a lowercase Greek letter sigma. This is the uppercase sigma, and it stands for sum, and we use it to write long sums in a compact form. And I'll show you an example. So, this might look weird at first if you haven't seen it before. We write the Greek letter with some stuff underneath it and above it, and something next to it. So I wrote sigma. Underneath it, I wrote k equals 1. Let me zoom in here. Underneath it, I wrote k equals 1. Above it, I wrote a lowercase n. And then to the right of it, I wrote a with a little subscript k. It's a with a little k down there. What this represents is the sum a1 plus a2 plus a3 plus ... It's a long sum, and it's actually going to go all the way up to an. So I guess we could say that the last two terms would be an minus 1 plus finally an. We call this sigma notation. K is called the index of the sum. So in this notation, let's talk about what these mean. Which one should we talk about first, actually? I kind of want to talk about the k equals 1 first. All right, so the k equals 1 means, and the n means, yeah, we'll do this like this. So the k equals 1 on the bottom is usually what I sort of look at first. And it means start at a1. And the n on top, which I usually look at last, it means stop at an. So that's why this equals a1, that's where we start, plus a2, plus ... all the way up to an. All right, so we start here and we stop here. So you could use this notation to add up 100 things or 1,000 things, or you could use it for small examples also. But where it's really powerful is when you have a really long sum and you want to add together like 100 things and you don't want to write them all out. So maybe you use this notation to make it like a nice compact thing, sigma of k equals 1, and then maybe up top it would say 100. Right, like n equals 100 if you're adding up 100 things. And then whatever, AK could actually be some other expression. So let's do some examples. This will help make it clearer. Examples of this notation. We'll do small examples at first. How about this? So I have sigma underneath it. It says k equals 3. On top of it, it says the number 5, and it says a k. So that's a small example of a sum that is written with sigma notation. And what this represents is simply a3 plus a4 plus a5. Period. That's it. Because the k equals 3 told me to start the sum at 3, the 5 up top told me to stop at 5, and we just go, with consecutive integers, 3, 4, 5, stop. And AK could actually be something else. We could have like a function of k, but for now it was just AK, so that's all we added. Let's do another one where we have something else. How about sigma? Underneath it, it says k equals 2. Above it, it says 6. And instead of AK, I'm going to say an expression involving k. It's going to be k squared. Just give you a chance in case you're writing that. I'll show you what this equals. So what this tells me, it says to take k squared, starting with k equals 2, and working our way up to k equals 6. And we're going to have something plus something plus something plus something, but the somethings are going to be the k squareds. So here's what we do. We start at 2, so we start with 2 squared. The next integer after 2 is 3, so 3 squared plus 4 squared plus 5 squared plus 6 squared, stop. That's what this represents. So this is like a compact way of saying what we did on the right-hand side. Of course, you could evaluate this. You could say this is 4 plus 9 plus 16 plus 25 plus 36. And you could figure out that this equals 90. So this actually does equal a number. It equals 90. I'll show you one more example for now. And then I might ask you to do little problems like this, where I give you something and I ask you to evaluate it. This one equaled 90. How about, I said something about adding together like 100 different things. So what we're going to do is k equals 1 to 100, and it's just going to say k. So what does this equal? Let's talk about this one together. Well, we start at 1, we end at 100, but the actual expression that we're evaluating is just k. Well, if k starts at 1, then you start with 1. And then what's the next one? It would be 2 plus 3 plus 4 plus dot. We put dot, dot, dot to kind of indicate that we're leaving out, like we're not writing all the terms, but eventually you would get to 99 and then 100, and that's where we stop. So this is the sum of the first 100 positive integers. And if you wrote them all out, it would take a long time. I guess the dot, dot, dot sort of helps us to abbreviate it, but the sigma notation is a nice compact way of writing it. All right, so I'm going to tell you that this actually equals, and you don't have to find this one by hand, but this one actually equals 5,050. In fact, if you're curious about how do you know this equals 5,050, there's actually a nice way to prove it. The proof is in the recommended textbook that we're following along with. If you're curious, you can look at that, or you could ask me about it sometime. But it's not super important for us to go over the proof of that right now. The main thing we're trying to do is just get used to this notation. All right, so I'm going to give you 2 examples to try, and they're going to be smaller examples. They're not going to be 100 things added together. So I'd like you to evaluate and simplify, sort of like the second example above where the answer was 90. I want you to do that sort of thing. The first one is going to be sigma. Underneath it, it says k equals 1. On top of it, it says 4. And this is 1 over k. And part B, sigma. Underneath it, it says k equals 5. And above it, it says 7. And it says parentheses k minus 1. So I'd like you to pause the video and try these. All right, let's move the old examples away. So for both of these, we should be able to just evaluate them to be an actual number. Our final answer should not have any k's in it. Final answer should just be a number. So this first one says start at 1, so we put k equals 1 in, and it's 1 over 1. And then you move on to the next integer, which is 2, and then the next integer, which is 3, and the next integer is 4, and you stop because it said to stop at 4. I guess we evaluated, but, you know, I told you to evaluate and simplify because I don't want to leave it like that. We could combine this into just one number. 1/2 plus 1/3 plus 1/4. How do you add those together? Find a common denominator. Common denominator of 12 works well. Right? We know how to add fractions. This is 12 over 12 plus 13 over 12. So final answer, 25 over 12. I guess it could be written as a decimal also, but I like 25 over 12. Next one tells us to start the sum at 5 and work our way up to 7. So it's not going very far. It's just going from 5 to 7. So like 5, 6, 7, right? But the thing that we're evaluating is k minus 1. So you start at 5 and you do 5 minus 1. So 5 minus 1 plus 6 minus 1 plus 7 minus 1. Stop. And we figure out whatever this equals. I guess this is 4 plus 5 plus 6. So I guess this is 15. All right, so that's the type of problem that I'm talking about. Just small sums using sigma notation for us to get comfortable with this notation. Now, this lesson is called sigma notation and Riemann sums. So you see that this notation can be used for lots of different types of sums. But in the previous lesson, we talked about Riemann sums, which were sums that we used to approximate areas. So in the previous lesson, we looked at f of x equals x squared. That was our main example, but you could also do other problems. Where the interval from 0 to 1 was partitioned into 4 subintervals of equal width one-fourth. I mean, if you divide that interval into 4 equal subintervals, then they have to have one-fourth as their width so that they all add up to the total distance of 1. And we drew the picture a bunch of times, but one last time we'll draw it. Real quick sketch. It looked like this, right? And we turned this into rectangles. And we showed a couple of different ways to do that, right? There was L4, there was R4, there was M4. And just to kind of recap those, R4 was 1/4 f of 1/4 plus f of 1/2 plus 1/4 f of 3/4 plus 1/4 f of 1 L4 was 1/4 f of 0 plus 1/4 times f of 1/4. All right, you probably have all of these in your notes from the previous lesson, but I actually wanted to write all 3 of these next to each other, because when we did them last time, they were kind of spread out throughout the lesson. And I said that all 3 of them looked similar, but now we're actually getting to see them just side by side. You see how all of these methods of chopping up those 4 subintervals into rectangles, the math that we're doing here, it's almost the same. It's just we're putting different things into F. So what I'd like to say about these is that each of these is, what if we write it in sigma notation? It's a sum of things. It's going to be sigma. Underneath it, I could say k equals 1. Up top, I could say n. And all of them are 1/4 times f of something. Now, what should we call the something? I mean, it was different for each of these. So I'm going to call it c with a little subscript k, where n equals 4, and C1, C2, C3, C4 are numbers chosen from the subintervals. Depending on whether we wanted right endpoints, left endpoints, or midpoints. That determined what the C's were. But other than that, they all have the same structure. They can all be kind of written with sigma notation with a 1/4 f of something. And I used the lowercase n for the number of rectangles, which, we mostly focused on n equals 4 rectangles, but you could also have a different number there. Now, in general, so that was a good, revisiting of what we did, and now we see that the sums that we were doing in the previous lesson could be written with sigma notation. In general, let f be a continuous function on the interval from a to b if the interval from a to b is partitioned into n subintervals of equal width, then the width is delta x equals b minus a over n. We said that formula last time. The area under the curve is approximately I'm going to use the letter S, capital S. All right, so the reason I'm using S is because I don't want to call it A. Because remember, like last time, we used a capital A for area, but when we used capital A, we were talking about the exact area. And right now, I'm talking about an approximation of that, so I don't want to use the same, I don't want to call it A, because we don't want to confuse this with the exact area. This is the approximate area, and it is sigma k equals 1 to n f of ck delta x. This, kind of goes with what we said above, where C1, C2, C3, C4, etc., they are numbers chosen from the subintervals. So you partition this into n subintervals, and you take C1, C2, and so on to be from the subintervals. Really, it looks like what we did above. It looks just like this. The only thing that's different is instead of saying 1/4, I'm saying delta x. And I guess I moved the delta x, instead of having it be out front, I kind of moved it over to the right. But, these are two things that are being multiplied by each other. F of something times this, and you can do them in either order. And we call this, you know what this is called already. We call this a Riemann sum. Now, in the previous lesson, towards the end of the lesson, I mentioned that we get more accurate estimates of area when we use more rectangles. The more rectangles we use, the better it is. So this sum might actually be really, really long. We might be adding 8 rectangles or 100 rectangles or 1,000 rectangles, and this could be a gigantic sum. And that's what makes this compact form very convenient. Instead of tons of things, it's just compacted into this. So this was kind of a shorter lesson. This is probably the shortest lesson of the whole semester, but the main point of this was to get you to be comfortable with sigma notation and to see that we can apply it to the types of sums that we were looking at in the previous lesson. And they're called Riemann sums, and they're used to approximate areas. Okay, so next time we'll continue talking about areas, and that's going to be it for now. So everybody take care, and I'll see you soon.